Hi Level 2s, a quick reminder, we've started electromagnetism, and during lesson 1 we looked at the basics of magnets, solenoids. We looked at what happens when we have a uniform field inside a horseshoe magnet, and also using a dot for the field coming out of the paper and a cross going into it. Then we've looked at magnetic fields around a current carrying conductor, wire. Using the wrap rule we can work out that the current strength, or the size of the current, the distance of the wire, and the permeating ability of the surrounding medium, how that will affect the strength of the magnetic field. We then also learned that you could use the right hand grip rule for wires, and where the thumb is the current and the fingers curling around is the magnetic field. We practiced with 2 of these in class. We looked at the solenoid. For the solenoid wrap, remember that the solenoid is, in this case, wound around by, there's copper wire wound around it, and that's the fingers then show the current direction, and this time the field is shown by the thumb, which points towards north. We looked at an electromagnet, and you had to complete some questions from activity 19A. I've adjusted the screen slightly, so for lesson 2, which is today's lesson, we're going to look at the force on a current carrying conductor in a magnetic field. So what we've got now we've got a current flowing through the wire. So it's not the field this time causing the current or the current causing the field. We've got both. A current in a wire and a magnetic field around that current carrying wire. And what happens is that the wire gets pushed out of the field. And this all again depends on 3 things: the strength of this field, the size of the current, and what the length is of the wire within the field. And we'll discuss that further in the next few slides. For now, you need to write this down. F equals BIL, where F is the force exerted, B is the magnetic field strength, I is the current strength, and L is the length of the wire inside the field. Please remember that the length of the wire inside the field can depend on either the magnet's width, or if the wire is shorter than the width of the magnets, then it's the wire's length. So in this little video clip here found on YouTube, you can see that this guy's connecting the wires. So that thing in the middle between the magnet, he's going to connect them the other way around now, and it kicks it out from between the magnetic. When I come back next week, I'll demonstrate this, but for now what you need to remember is that there's 2 versions of the right hand slap rule. Pardon me. So we've looked at the one on the left, where a magnetic field, the magnetic field direction, remember, is always where the fingers are, and the cause of whatever's happening in this case is the current, and the force is the slap. But there's also the induced current from motion. So here you've got the magnetic field, direction of movement is the cause, and direction of the current is the effect. So which one works for the kicking wire is the one on the left. We get motion because as soon as the current is connected, there is a force on the wire and it's kicked out. So here's the first example. There's an aluminium rod of 7 centimeters. It's 7 centimeters long. It's resting on rails. These are connected to the positive and negative terminal of the battery. The rod and rails are inside this magnetic field here. A strength of 2 Tesla. When the supply is turned on, a current of 3 amps will flow. So obviously it flows from the positive terminal and then down from left to right across this rod and down to the negative terminal. Question is, what is the direction of the magnetic field? And identify which pole is north and south if the force is acting to where the green arrow shows. And the answer using Fleming's left-hand rule is that the North Pole will be at the bottom. and the South Pole will be at the top. So what you need to do here, and this is going to be a little bit difficult to show you without standing in front of you, but if you imagine that your thumb is the current direction, so that doesn't change. You have to go sort of from left to right, but either your fingers can go up or your fingers can go down. Then there's only one way for it to cause a force outwards, and that is if the palm of your hand is beneath and the tips of your fingers are at the top, so that the force acts outwards. In other words, the way the green arrow is showing. So try it first for yourself. If you can't get it right, I'll help you in class. The next question asks you to find the strength of the force on the wire. So you've got the current, the magnetic field, and the length of the wire. Remember to convert centimeters to meters. Using F equals BIL, you then find the force is 0.42 newtons. Right, so what you need to do here now is go through A, B, C, and D, and for each of them try to work out if the rod will move in each case. So the rod is free moving on the rails. Work out which way it will be forced. Will it go back towards the magnet or out of the magnet in each of the cases? And before you move on, you must try it yourself. So I hope you've paused the video and tried it yourself. In each of them, you work out which is the current direction first. Obviously draw the field in, and if you still haven't tried now, try this yourself. Pause the video and determine which way the force is produced using the right hand slap rule. And here are the answers. For A, it's towards the magnet. For B, it's away from the magnet, and C, the same. For D, however, there's no force because the field actually runs the same direction or parallel to the current in the rod. Right, you now need to complete 19B, questions 1, 3, 5, and 7 in your class time on Monday in class.